Okay, so today I'm going to just continue talking about dynamical consequences of symmetry, and I'm going to discuss two examples. So first of all, I will continue to discuss the previous example about U1 times U1 symmetry. So the first example is U1 times U1 symmetry in 1 plus 1D. And for the second examples, there are like two sub-examples. So for the second example, I'm going to discuss the symmetries described by a bulk Z2 gauge theory. Okay. So let me begin with the first one. So recall last time we talked about the symmetries of a compact boson in 1 plus 1 dimension. So there's U1 winding symmetry and U1 momentum symmetry. Well, let me first draw a line. And those U1 times U1 symmetry has they have a mixed anomaly, and the mixed anomaly is described by a bulk theory. So there's a 2 plus 1 the bulk theory. So let me just write down the bulk action. Okay. So here, this AWAM are the background gauge field for the U1 winding symmetry and U1 momentum symmetry. Okay. So last time I gave an argument that if you have a 1 plus 1D system with this kind of anomalous U1 times U1 symmetries, then the system has to be godless. Okay. So today I'm going to present another argument. So let me first write down a claim. So if you have a 1 plus 1D system with a U1 times U1 symmetries, and such that it has this particular anomaly described by this particular bulk theory, anomalous symmetry. The system has to be godless. Okay. Okay, so maybe well, let's see. Maybe let me write the bulk theory here. So described by the bulk theory. 1/2 pi a winding dA momentum. Okay. Okay. So this particular bulk theory that describes the anomaly tells you that if you perform a transformation of the winding symmetry, or maybe, well, maybe let me do it another way around. So let me just exchange Wm here. So this is the momentum symmetry, and this is winding symmetry. So if you perform a transformation of the U1 momentum symmetry, so you change the gauge field by d alpha, then the boundary will pick up a phase. So the Poisson function on the boundary will change to boundary, and then lead to the integral of I over 2 pi and alpha dAw. Okay. So this is just Stokes theorem. So now let's consider a particular case where alpha is a constant. So take alpha to be constant. Now, if alpha is a constant, then this transformation is a global symmetry transformation. Global symmetry transformation. And under a global symmetry transformation, the Poisson function should be invariant. So that tells you that we actually have a equality, like z boundary equal to z boundary, and then e I alpha over 2 pi integral of dA w. Okay. Now, if we consider a magnetic flux of the U1 winding symmetry such that the integral of the U1 winding symmetry on the space, well, on the 2D boundary, is like 2 pi times the integer m. Okay. then this tells you that Z boundary equals to Z boundary multiplied by e to the I alpha times n. Okay. Now alpha is arbitrary, so it's a constant, but it's arbitrary real constant. And in particular, alpha does not have to be any 2 pi times integer. And therefore, in such case, you find out the boundary Poisson function actually vanishes. Okay. So if alpha is not 2 pi over n times integer, then you find out the Poisson function actually vanishes. Okay. And we can take the boundary to be to have a space-time topology of S2. So let's take the space-time for the 1 plus 1D system to be topologically equivalent to a 2-sphere. Okay. And we find out the boundary, the Poisson function on 2-sphere will have to be 0. Okay. Now, in general, if you have a vanishing Poisson function, the system can be gapped or gapless. So, but I'm going to argue that if you can turn arbitrary flux, then the system has to be gapless. Okay. Now, the idea is that the Poisson function on the 2-sphere is equivalent to a so you can think of it as a inner product between the state from the like this on the, or maybe let me divide the sphere by upper and lower part. So this is so there's a north part and the south part. Okay, and the Poisson function on the sphere is generally a like inner product of the state on the north hemisphere and the state on the south hemisphere. Okay, and suppose the system is gapped, then there are multiple ground states. So in general, there are many states on the north hemisphere and many states on the south hemisphere, and the Poisson function has to sum over all the ground states. Okay. Now this is the Poisson function in the absence of any flux. So this is the Poisson function when n equal to 0. When the flux is non-zero, the Poisson function is equivalent to the exponential value of the flux correlation operator. Okay. So how do you get a background that has non-zero flux? So one way to get a background is to glue the 2 hemispheres by a gauge transformation along the equator. So you can label the coordinate on the equator as some angular coordinate theta. And the way to get a flux with 2 pi times n is to glue the 2 hemispheres by a gauge transformation for the U1 winding symmetry. It's given by the label n times theta. So here we perform a transformation. So there's a U1 winding transformation given by e to the in times theta. Okay, so theta is the coordinate along the equator. Okay. So and that's denote the operator. So let me just invent an operator which implement the transformation given by e to I theta along the equator. Then the Poisson function with flux is the matrix element of this operator. So it's sum over. So this here I labels the ground states in the system. So this sum over I and e to I theta. Well, maybe let me just write down a t here. And just write down t here. And then you just evaluate the exponential value of this like gauge transformation operator along the equator. Okay. Now, suppose the system is gapped with finite many ground states. So suppose the system is gapped with finite number of ground states. Now I should mention that here I'm going to assume that any well-defined gap system must have like finite number of ground states because otherwise the free energy will be infinite. Finite number of ground states. then you will have a contradiction. So let me derive contradictions here. So you notice that this operator implements the gauge transformation e to I theta, where theta is the coordinate labeled equator, and this operator, so T generates a integer group, so it generates a cyclic group by like just taking power of T. Okay. And moreover, this operator will induce a map on the space of ground state in your gap system. So T will induce a map. Maybe I should just say that T T induces a representation on the ground state. Okay. So this operator, so itself generates a cyclic group, infinite cyclic group, but it generates a representation on the ground state. Now, if there are finite number of ground states, then this representation has to be finite dimensional. And if you want to have a finite dimensional representation of a infinitely cyclic group, then the representation cannot be faithful. So, because the number of ground states is finite, so the representation is cannot be faithful. That tells you that there exists an integer n such that the action of T on a ground state to the power n is equivalent to identity. Okay. Just because the number of ground states is finite. Now, therefore, well, if you consider a flux which is 2 pi times like a integer multiple of 2 pi times n. So suppose this n is actually, so let's just say n times some additional integer. Maybe I'll just put n here. Then the Po-Shen function on the sphere is the exponential value of t to n. But t to n acting on the ground state is equivalent to 1. So you'll find out this is a sum of the inner product of the ground state. All right. So, but the inner product of ground states has to be non-zero, and therefore we have a contradiction. So this anomaly tells you that if you turn a background flux for a one winding symmetry given by 2 pi times n, and you perform like general transformation from a V1 momentum symmetry given by alpha, then you conclude that the Po-Shen function vanishes in this particular background. But then you find that if you have a gap system in one Po-Shen dimension with finite number of ground states, the Po-Shen function on H2 with this particular background cannot be 0. So you have a contradiction. So then you conclude that the system has to be gapless. Okay. Okay, so that's the first. Well, that's another argument that if you have a U1 times U1 symmetry with this particular anomaly described by this bulk theory in 2 + 1 dimension, then the system has to be gapless. Okay.
So the anomaly theory involves obviously the anomaly with the 2D bosons.
Yeah.
And that's what you wrote down. I don't understand when you wrote down position, and you say Z product of states on S1.
Yeah.
I don't understand why you're not insert T operator and how that's related to the diagonal theory.
Right. So if you want to construct the background on H2 such that it has a 2 pi times integer flux, so what you to engineer is that you perform a sort of, well, so maybe I should write down an example of such background. I should erase something. Maybe let me just erase this. So you have a system with U1 times U1 symmetry. Now how do you insert a magnetic flux given by 2 pi times n? So one way is to perform the following symmetry transformation. So it's going to be a local transformation. So let's say this is your space, like this is periodic. So 1D space which is periodic. So the coordinate is theta. And the transformation I'm performing is equally in times theta. So it's different transformation at different points along this space. Yeah. So if you perform this transformation, then you flat the space by this flux. Yeah. So let's, yeah. Well, yeah. Okay. So now I'm going to discuss another example. So before I just switch gear, are there other questions about this particular example? Okay, maybe then I can erase everything. So now I'm going to discuss 1+1D system with Z2 symmetry. Okay. So let's consider 1+1D system with Z2 symmetry. Z2 symmetry. Okay. And the symmetry can be described by a theory in the 2+1D bulk, which is given by a Z2 gauge theory. In 2+1D. Okay. So let me first tell you a little bit more about the Z2 gauge theory in 2+1 dimension. So you can describe the Z2 gauge theory by a pair of U1 gauge theory. So I'm going to call a pair of the gauge field A and B. So can this be described by this action where A and B are U1 gauge field. And I'm going to declare that A is my Z2 gauge field. And the reason it's a Z2 gauge field is that B is a Lagrangian multiplier that constrains A to have holonomy 0 and pi. So B constraint, let me just write down a holonomy of A is like 0 pi. Okay. And similarly, I'm going to call B as my dual Z2 gauge field or the magnetic gauge field. Okay. Okay, so if you have a 1+1D system with this 2+1D gauge theory, I can describe the symmetry in the following way. Okay. So okay, so this is going to be my 1+1D system, and this is my Z2 gauge theory. Okay. So in the book, the Z2 symmetry is gauged, so that's why you have a Z2 gauge theory. Now, in order to get a 1+1D system with a Z2 global symmetry, I have to impose a Dirichlet boundary condition. Okay. And one way to think about this is that I put the Z2 gauge theory on a slab. On one boundary, I put my original 1+1D system. On the other boundary, I'm going to put the Dirichlet boundary condition, so equal to 0 on the boundary. So recall that here I choose A to be my Z2 gauge field. So this is my Z2 gauge field. Okay. So that's a system with a Z2. So this slab is going to describe a 1+1D system with Z2 global symmetry. And the reason is that this Z2 gauge theory is topological, so it can shrink the slab such that the whole system reduced to 1+1 dimension. Now, similarly, I can describe the theory such that the Z2 gauge theory, such that the Z2 symmetry is gauged. And the way is to similarly put the original 1+1D system on one boundary. some consistent. And then in the book, I also have the same Z2 gauge theory. But the other boundary is going to be the free boundary condition or the Dirichlet boundary condition of the dual Z2 gauge field. Okay. Now, because if I impose this boundary condition, the gauge field, the Z2 gauge field is still non-trivial on the boundary. So that tells you that if you start from this picture and then shrink the bulk, you'll land on 1 plus 1D system where the Z2 symmetry is gauged. Okay, so let's give you 1 plus 1D system with Z2 gauged. Okay, so this is 1 plus 1D system. So this is the original 1 plus 1D system with Z2 symmetry. Okay. So how does the Z2 gauge theory describe the symmetry? Well, so in this system that describes the system with Z2 symmetry, because I impose the Dirichlet boundary condition for A, so the symmetry is going to be described by the remaining gauge field B. Okay. So in this theory, there are the following operators. So there are Wilson operator given by the Wilson of A. So I'm going to let me just give you a name. So let me just call it W. So W is going to be the Wilson of A. Okay. And then I'm going to denote capital M to be the Wilson of B. Okay. Now, for this particular boundary condition, the Wilson of A does not exist on the boundary. But I still have the Wilson of B. And this Wilson of B is going to generate the Z2 symmetry on the boundary. So this is the Z2 symmetry in 1 plus 1D. Okay. And the reason it generates the Z2 symmetry in 1 plus 1D is because there's a braiding between the Wilson of A and Wilson of B. So you have a, well, let me first draw a braiding picture in the bulk. So if you have a link which is W and the other is M. So suppose you have a Wilson loop of W, a Wilson loop M, such that they link together in 2 plus 1 dimension. Then this linking gives you a -1. Okay. Now, if you have this boundary condition, then you can have a Wilson line of A that ends on the boundary because you have a Dirichlet boundary condition there. So a Dirichlet boundary condition there. So this is the 0. And this endpoint will carry the Z2 global symmetry. So Z2 symmetry. And a way to see this is that you can bring a Wilson of B, which is parallel to the boundary, such that it crosses this endpoint. So just, well, maybe I should change color. Can just bring it like cross this point. Maybe let me just draw a new line here. So this is B. And because the braiding between the Wilson of A, so this is the Wilson of A, and this is Wilson of B. And because the braiding between the Wilson of A and Wilson of B, it tells you that if you slide this line operator across the endpoint here, you'll get a -1. Okay. So this tells you that the endpoint will transform under the Z2 symmetry. Okay. So that's a manifestation of the Z2 symmetry in the system. Okay, so now we have a description of the Z2 symmetry using the Z2 gauge theory. We can ask the question, like, can we learn anything about dynamics? Okay. So first of all, I'm going to say that, so first of all, you can have a trivial system. with Z2 symmetry in 1% D. Okay. Now, this statement is intuitively true, and now let me show you how to get this statement from the Z2 gauge theory. So I'm going to engineer a trivial system using the Z2 gauge theory. So I start from the Z2 gauge theory in 2-Poisson dimension. And on one of the boundary, I'm going to choose the Dirichlet boundary condition for A. Okay. Well, for the other boundary, I'm going to choose the Dirichlet boundary condition for B. Okay. Now, in this particular system with these particular boundary conditions, if you shrink the bulk, it's going to kill the degree of freedom because here I choose the Dirichlet boundary condition of A and Dirichlet boundary condition of B, and therefore this gives you a trivial system in 1% D. Okay. So let me just say a little bit more about this particular construction. So if you have a Dirichlet boundary condition for A, it tells you that you can have a Western line of A, namely this W operator that ends on the boundary. But the Western line operator for B, and namely this M operator, cannot end on the boundary, so you must turn somewhere. And similarly, if you have a Dirichlet boundary condition for B, it tells you that the Western operator for B can end on the boundary, or it can have M ending on boundary. But the Western operator for A cannot end on boundary. So this is W. Okay. And therefore, for this particular boundary conditions, there is nothing that can extend between the two boundaries. And therefore, as you sort of pass the whole step, you just kill every observables. Okay, so nothing can end on two boundaries. Okay. Okay, so having a Z2 symmetry is not sufficient to give you any dynamical constraint. So we should add more symmetries. So is this clear? Is everything okay so far? Okay, I'm going to erase everything here. Okay, so the Z2 gauge theory, described by this gauge field A and B, has another symmetry, which is called the electromagnetic duality symmetry. Okay, and this electromagnetic duality symmetry simply exchange A with B. Okay, so here I'm going to call the so because here I choose A to be my Z2 gauge field. So W is the Wilson line that describes the electric particle, and N, which is the Wilson line of this dual gauge field B, is going to describe the magnetic particle. So they are one line of some magnetic probe particles. Okay. So that's why this is called electric magnetic symmetry. So in particular, it has the feature that because the symmetry is going to be generated by a domain wall in 2-Poisson gauge theory, and the domain wall has a feature that if you have a Wilson line of W, so let me just label it by E. If this Wilson line pierces the domain wall, it's going to transform into Wilson line of B, namely magnetic particle. So I'll just call E and M. So what's the property? Well, so what's the property of the domain one? Now maybe before going to a property, so if you have a domain wall in the Z2 gauge theory, so the way the domain wall can induce a symmetry on a boundary is by ending a domain wall on the boundary. So if you have a domain wall, well, I should use a different color. So so if you have a domain wall or surface in the 2+1D theory, the way it describes symmetry on the boundary is by ending the domain wall on the boundary. So new symmetry. So we should consider domain wall with boundary. So imagine the let me just cut the boundary somewhere. So let's see. Okay, maybe let me draw it the other way, the other ball. Okay, so let's consider domain wall with boundary. Okay, and here you have a Wilson of A, like coming to the domain wall and then transferring to Wilson of B. Okay, and then we put a boundary here. So this is a domain wall. And imagine this is a surface. Okay. So because well, I should first say that all those Wilson lines are topological because the field strength locally vanishes. So W and N are topological because if you deform the Wilson a little bit, it's going to change by dA and dB, and they locally vanishes. Okay, so you can just freely deform those Wilson lines. Okay. Now you start from this configuration where the Wilson line W enter this domain wall that drains the electromagnetic duality symmetry, and then it becomes the Wilson line of B, the multi-particle. Now you can sort of try to pick up the two ends of these two lines and try to pull it down. And if you pull it down, you got the well, let me use different color. So E is like yellow, okay, and it's like white. So let me just put it here. Okay. So because you can freely move the well, maybe let me further pull it down. So not just at this point, but at the end point here. So this is my E, and this is my N. Okay. So the way you should think about this picture is the following. So first of all, this is really a surface. I'm not sure how to draw it. This is like, so let's see. This is like a surface. Okay. And there's a boundary given by a line. Actually, it's a different color. So there's a boundary given by a line. And you should think of the surface as like extending in all the other directions, but there's a boundary. Okay. And then, so let me just draw the picture here. And let me just draw the picture. Just show you a better way. So you have a boundary here. Can be kind of busy. So you gradually pull this two operator down. Okay. So this is your surface and this is the boundary. And then until until it becomes the following configuration. Okay, so it becomes this. You have an E here and M here. Okay. Okay. So what does it tell you? So first of all, let me give the boundary a name. So I'm going to call the boundary sigma. So this tells you that you have a junction between this boundary line operator sigma and the Western line and two-fly operator. Okay. So this is the fusion of the Western line two-fly. So I'm going to give you a new name as f. And here f is because this composite of E and M is actually fermion because the braiding between the Western line two-fly. So f is actually a fermion. So this junction tells you that you have the following fusion rule. So maybe let me erase something. Let's see. I can use this? Okay. So so this junction tells you have the following fusion rule. So sigma times f equal to sigma. So the reason is that you have a sigma here, and it is joined by this f, which is the composite of E and M. But then it also you come up with the same sigma again. Okay. Now on the other hand, there's also another fusion rule, namely, so if you just look at the sigma line here, then you have a let me just separate these two pictures a little bit. So you have this sigma line here, and then it's ended this joined by a trivial line. So there's an identity operator here, and it's joined by the trivial line, and still come out with the same sigma again. So therefore, you actually have the following fusion channel. So first we have this fusion rule coming from this picture. Another picture is sigma times sigma equal to 1 plus f. Okay. So the one channel is described by this picture, where you can think of this picture another way, that you join two sigma into the trivial line, and here you join the two sigma with the fermion line. So this is the second fusion channel. Okay, so right. So first of all, is it clear to you? Like I got this junction. Okay. So you have two kind of junctions. So one is the junction, this kind of junction I just told you. Another junction is more trivial, namely if you just have a single sigma, and it's ended by a trivial line, and just means that you just have a single sigma line. Now you can interpret these pictures in many ways. So one way is that you start with a sigma and fuse with the trivial line. You still got sigma, and this is kind of trivial. And similar here, you start with sigma, and then you fuse with this f. So the composite of E and M is f, and then you still got sigma. Okay, so that's one way to interpret this junction. So this is basically the first equation. Another way is that you start with a sigma here, sigma there, and then you fuse into the trivial line, right? And here, this way of interpretation is that you start with sigma here, a sigma there, and then they fuse into the fermion line. Okay, so that's why you have these two fusion channels here. Yeah.
When you use the sigmas, you don't have to worry about the lattice surfaces.
Well, here this is just a fusion rule about this boundary. Yeah. Yeah. Mm-hmm. Oh yeah, we don't worry. I mean the surface is here. The surface is fixed, right? So this fusion rule is just interpretation of this picture. Yeah, yeah. So are there other questions about the fusion rule? Okay. So this tells you that if the if the electromagnetic duality symmetry surface ends on the boundary, so the boundary is going to be this sigma line. So this is, I'm gonna use this orange color. So this new symmetry is the sigma. This new symmetry is going to obey this kind of fusion rule. Okay. Now here, because to construct the 1 plus 1D system, if you want to get a 1 plus 1D system with a additional Z2 symmetry, we have to impose the Dirichlet boundary condition of the Z2 gauge field. And if you impose the Dirichlet boundary condition of the gauge field, then this W line will become trivial. And then, so if you are ending on the boundary, you impose the disciplinary condition for the Z2 gauge field. So that means that this W and N actually just becomes N. Okay. So now so I'm going to call the this, well, let me just say that you have sigma times sigma equals 1 plus N. So N is the Z2 symmetry. Okay. So the boundary will have two kinds of symmetries. One is the Z2 symmetry, which is this M. The other kind of symmetry is the sigma here, such that you obey this kind of fusion rule. Now, this fusion rule does not have, this fusion rule tells you that the sigma symmetry does not have an inverse. So this is usually called non-invertible symmetry. Maybe I should erase this. So, so sigma, it does not have an inverse, does not have an inverse. So this is called non-invertible symmetry. Non-invertible symmetry. Okay. So this is just terminology. Now, in general, this conjunction does not really give you a symmetry, but only give you an interface. So let's look at what happened on the boundary. So this is your 1 plus 1D boundary, and then here this is your 2 plus 1D bulk. Okay. Maybe let me just, this is like a surface. I don't know how to draw it. It's like a surface. Okay. And the okay. So in general, when this electromagnetic duality symmetry ends on a boundary, so this is the surface that drains the electromagnetic duality symmetry, and you can have this orange line. So this is your new symmetry sigma. Okay. So in general, you will have different kind of theory on the boundary. So what are the theory on the boundary? Well, you notice that this electromagnetic duality symmetry exchange A with B. Okay. So this means that if you okay, let me try to draw a 3D picture. So imagine there's a surface here. So if you start with a theory here by imposing the Dirichlet boundary condition for A. Now, because you have this electromagnetic duality symmetry that swap A and B, so here you are going to impose the Dirichlet boundary condition for B. Okay. Now, in general, you will have the resulting system will be a combination of two 1 plus D systems separated by a domain wall. Okay. So we have one system living on the upper part, and the other system living on the lower part. Okay. Now, what's the relation between these two systems? Well, as I told you earlier, if you impose the Dirichlet boundary condition for A here, you'll get a system with Z2 symmetry. But if you impose the Dirichlet boundary condition for B, you are going to get a system where the Z2 symmetry is gauged. So we have a Z2 symmetry and Z2 gauged. I should write it better. Z2 gauged. Okay. So if you want this sigma to be a symmetry in a single theory, it tells you that the theory has to be invariant under gauging the Z2 symmetry, because the system with Z2 symmetry has to be the same as the system where the Z2 symmetry is gauged. Okay. So let me just write down the statement here just to summarize. Let me just erase here. Okay. Okay, I guess I can also erase the thing here. So if you, the statement is the following. So if I have a one-Poisson D system with a Z2 with a symmetry M and the sigma such that M squared equal to 1, so it generates a Z2 symmetry, and sigma times sigma equals to 1 plus M. Then the system will be invariant under Gauge Z2 symmetry. The system will be system will be invariant under gauging Z2 symmetry. Okay, so that's the first statement. So what are the possible dynamics of this kind of system with this symmetry sigma and symmetry M? Okay. So previously we said that if you just have a Z2 symmetry M, then the system can be trivial. But now you add another symmetry sigma, so maybe there's no there are more non-trivial dynamics. Okay. So again, we can describe the dynamics using a 2+1D system. This is the D2 gauge theory. And here is our one-Poisson D system with the symmetry sigma M. Sigma and M. Now recall that the way we construct the we construct a trivial system with Z2 symmetry is by imposing boundary conditions. So we can have original system here, and then here we can choose either D-shaped boundary condition for A, like the 0, or B equal to 0. Okay. Now, however, those boundary conditions that we use to construct a trivial system are not invariant under the electromagnetic duality symmetry. So, not invariant under the electromagnetic duality symmetry. Okay. And therefore, if you have a system with both the sigma symmetry and the Z2 symmetry M, the dynamics cannot be trivial, because you cannot construct any trivial dynamics by imposing like Dirichlet boundary condition or the for A or B, because either of them is not invariant under the electromagnetic duality symmetry. So this tells you that the system will in fact has to either spontaneously break the sigma symmetry, or has to be gapless. Okay. So here we show that if you add additional symmetry, this symmetry sigma, you can derive dynamical constraint on the system. So the system can no longer be trivial if you include additional symmetry. But if you break this new symmetry, then you can again get a trivial system. Okay. So let's see. I think this is a natural stopping point. So are there any questions about the argument? So later I'm going to discuss lattice model, like lattice version of the discussion. Okay. So maybe we can have a break here, like for 10 minutes or so. Okay, so I'm going to give you an example, just the critical Ising model in one-Poisson dimension that has this sigma and M symmetry. So example of one-Poisson D system with sigma times sigma equal to 1 plus M. Okay. So let me give you a lattice model where you have a again, I'm going to take a lattice to be infinite, and each side has a qubit, has a z2 degree of freedom. So each side has a z2 degree of freedom that is acted by the poly x poly z operator. So poly operators. Okay. So it's going to be the very similar to the spin chain model we discussed last time, but there's an additional transverse field. So maybe let me write the model here. So so the size, I'm going to label a size by I. So I runs from like 1 to 3, etc. And Hamiltonian is the following. So minus j zi plus 1. And I'm going to introduce another coupling, which I call tau, which is sum over xi. Okay. So, so this model is consists of like two types of term, and they do not commute with each other because the poly z and poly x operators do not commute with each other, and therefore I have to specify the coefficients here. So, well, I only have to specify the ratio of the coefficient, but here the coefficients are j and tau. Okay. So the model has a Z2 symmetry. So Z2 symmetry. So this symmetry is given by the product of the poly x operator over all the sides. Okay. So and the symmetry commute with the Hamiltonian because the poly x commute with poly x, and then for this term you have even number of poly z. So it also commutes with this symmetry. Okay. So H is equal to Hn and m squared equal to 1. Okay. So I'm going to gauge the Z2 symmetry. I'm going to gauge the Z2 symmetry. So I'm going to use the traditional way to gauge the Z2 symmetry. Now there are some discussion about gauging using some kind of gauging map, but I'm not going to do that. So I'm going to introduce a degree of freedom for the gauge field and then perform gauge fixing. So the gauge degree of freedom is going to live on links. So let me draw the lattice again. So let's say this is your like the sides labeled by I, okay? And the links are labeled by, so let's say I equal to 1, 2, 3 are the sides. And the link can be labeled by like half integer I. So like I equal to half is between the 0, is the link between 0 and 1. Okay. So so I'm going to introduce the gauge field living on links. And in particular, I'm going to impose Gauss law. So if you just have a Z2 symmetry, then the Gauss law consists of the poly X operator because that's just the how the Z2 symmetry is defined. But now because I introduce another additional degree of freedom on a link, so the Gauss law is modified. So I'm going to denote the poly operators acting on the QB on the links with a tilde. So on the side I have xi and zi, and on the link I have a I have xi plus a half. Well, maybe here I should put minus with a tilde, and then z tilde I plus a half. So this is minus. Minus a half, okay. So, and this is the Gauss law. So I have xi here for the size here, and then I have x tilde I minus a half here, x tilde I plus a half here. Okay. So these two x tildes are on the neighboring links. So this is like here and there. So this is my x tilde, and then xi is at the side I. Okay. So this is the Gauss law. And I'm going to impose the Gauss law. Namely, I'm going to set this combination of operators equal to 1. Okay. So that's the first thing. And then I'm going to modify the Hamiltonian such that it commutes with the Gauss law operator. So we have to modify the Hamiltonian such that it commutes with the Gauss law operator. Okay. So for the poly X operator, we don't have to worry because poly X automatically commute the Gauss law. But for this product of poly Z operators, by itself, it does not commute with the Gauss law operator. And because it does not commute with the poly X operator at each site. However, we can modify this product of poly Z as follows. So I can use this, okay? So modify. So this is going to be the following. So this is minus J. We'll have Zi. Oh, maybe let me write it slightly here. So let me just write smaller. So there's a minus J, and then, well, okay, let me just write smaller. So there's a Zi, and Zi plus 1. Okay, so that's the original term in the Hamiltonian. But now I have another term. So this another term is Z tilde, well, this I plus a half. So, so I can think of this Z tilde as a small Wilson line. So you have a like Zi here and Zi there, Zi plus 1 there. And this Z tilde is a small Wilson line, not extend between the two sides. So you have a Z tilde plus a half here, Okay. And once you modify the Hamiltonian term this way, it automatically commutes with the Gauss law operator. And this is because, like whenever this poly Z operator overlap with the this poly X operator on the side, the poly Z tilde operator will overlap with the poly X tilde operator. So we have two minus sign in the commutation relation, and you have plus 1. Like this term commute with the Gauss law operator. Okay. And again, let me just copy the other term minus tau. This is xi. Okay. Okay. So this is the final theory after we gauge the symmetry, and then we first impose this Gauss law operator, and then we modify the Hamiltonian this way. Okay. But we can further simplify the theory. Okay. So first of all, because you have this Gauss law constraint, we can replace all the poly X operator by the X tilde operator. So I can erase this X here, and then replace it by the product of X tilde operator. So this is going to be X tilde I minus a half, X tilde I plus a half. Okay. And this is because I have this constraint here. Okay. Now, furthermore, I can use this constraint to gauge fix the degree of freedom on the side to be trivial. Okay. So because this constraint has a single poly X on each side, so I can always use this constraint to choose the degree of freedom on each side to be like flipping up, for example. Okay. So I can use this Gauss law operator to remove the degree of freedom on the side I. So I can use the Gauss law to remove or gauge fix the I degree of freedom.
But before you impose the input, what's the gauge symmetry? So that doesn't change, and that can change to sign.
So the symmetry is this Gauss law operator. So this Gauss law operator is like local symmetry. So previously you have a global Z2 symmetry. Sorry?
How it acts on the I side?
Right. So, I mean, so this is your local symmetry. Actually, it does not. Yeah. For the zi, anti-commute this local Gauss operator. So therefore, zi will transform into minus zi. Yeah. Yeah. Oh, okay. Let me say a little bit more. So what's the transformation imposed by this Gauss law operator? So you have if you have a single you have a single zi, and if you have a single zi, you will flip sign under conjugation by this, right? I have it. Okay, sorry. Yeah. So not just this single zi, but if you have any like z tilde, for example, you also intercommute this. Yeah. So in a way, so this Gauss law constraint sort of correlate the gauge transformation for the tilde degree of freedom on the edge and the untilted degree of freedom on the side. Yeah. And it's the local version of the original Z2 global symmetry. So if you take product of the Gauss law constraint, if you take product of this Gauss law operator, all the x tail will cancel each other, and then you just got a product of x. That's the original Z2 global symmetry. So this is the local version of the original Z2 global symmetry. Yeah. Okay. So and if you because we impose this Gauss law constraint, we can use this to gauge fix or remove the degree of freedom on the side. So we can use this constraint to make sure that all the degree, all the QB on the side are like, for example, pointing like spin up. So in this way, we can remove all the poly operator. So we can erase all the poly operator. Okay. So what's the new? So this is the new Hamiltonian we got. So it's a sum of the this poly z tilde operator, and also the sum of product of poly x tilde operator. Now this is basically the original Hamiltonian with the z and x swap. So we can rotate the z to x by some single cubic rotation on all the sides. But importantly, the coefficient between this quadratic term and this linear term are swapped. So originally, J is the coefficient for this quadratic term, and tau is the coefficient of this linear term. But now you find out this J becomes the coefficient of linear term, and tau becomes the coefficient of the quadratic term. Okay. So basically, this gauging tells you that. So this is related to. Well, maybe let me first. Okay, let me just erase this. So if you gauge the Z2 symmetry, you got a model with J and tau swapped. Okay. And in particular, if you tune the coefficient to be J equal to tau, so if like J equal to tau, the system is invariant under gauging the Z2 symmetry. And because in this particular case, the system is invariant under gauging the Z2 symmetry, the system has the sigma symmetry. Okay. Are there any questions at this point? Right. So you can explicitly write down expression for sigma. It's kind of complicated, but it's. I mean, there's an explicit expression for that. Yeah. I mean, just. So for CFT, well, I mean, for symmetry, sigma is like one of the Varinda line operator. Yeah. So I mean, if you go to the continuum limit, you have some Ising CFT. So you have various line operator, various primary. Yeah. And they will be the line operator correspond to the sigma. Yeah. Yeah. I mean, that's why I use the name sigma here. Yeah.
Can you add a term such that the Z2 symmetry is spontaneously broken? You still do not get sigma symmetry. The sigma symmetry is spontaneously.
So you want to break which one? Sigma or sigma? You want to break sigma? Well, in principle, it's possible. Yeah, I mean, you can have a broken symmetry that fuse into unbroken symmetry. So in principle, it's possible. Yeah. Okay, so so this is the model, and because of this general constraint we derived earlier, we can use this symmetry sigma and m to constrain the dynamics of the system. And for the easy model, well, because we already know dynamics, we know it's actually gapless. But if you add any deformation, you can potentially bring it to a state a system where the sigma is broken. Yeah. I mean, for example, if you maybe let me not give you an explicit example. Yeah. So that's one example. So now I'm going to discuss the lattice construction of the Z2 gauge theory. Okay, so I'm going to erase everything here. Oh. So, so I'm going to do what I'm going to do now is to give you a lattice construction of the this 2% DZ2 gauge theory and a lattice construction for those Dirichlet boundary conditions. I'm going to interpret this boundary condition as the condensation of some excitation. Okay. Okay. So the most classic construction for the Z2 gauge theory is the torical model. So torical model for 2% DZ2 gauge theory. Okay. So you can define the model on arbitrary triangulated lattice, but let's just take the lattice to be a square lattice. Okay, so I'm just sketch some the square. Okay, so this is a 2D square lattice, and I'm going to put my degree of freedom on the edge. So I have qubit on each edge. So just draw a circle here. Okay. And this degree of freedom are acted by the poly Z and poly X operator. And I have the following Hamiltonian. Okay. So I'm going to use the poly Z as my gauge field. So the eigenvalue of poly Z on some edge, so E is the edge, labels the gauge field. Okay. So, and because the poly X and poly Z anti-commute with each other, I should have a longer chalk. It's here. Okay. So because the poly X anti-commute with the poly Z, so poly X describe the electric field. So you can think of that electric field. Okay. And the Hamiltonian has two terms. So one term imposes the Gauss law constraint. So there's a Gauss law term. So one term tells you that at low energy, you must have states satisfy the Gauss law. Okay. And the other term, it tells you that at low energy, there's no flux of the gauge field, because you want to have a flat gauge field. Okay. So what does the Gauss law operator look like? Well, the Gauss law is basically like -1 to the divergence of the electric field. So electric field, let me just call it E. And so at a single point, the divergence of the electric field is given by the products of the poly X operator for the edge that touch this point. So let me call the point as vertex V, and then I have a product of poly X operator on the edge adjacent to this vertex V. Okay, so I have a sum over vertices, and then a product of poly X, where the product is given by this 4x. Okay. Now, because the polyzero operator is the Wilson line, so the flux is going to be a small Wilson loop. So, for example, if you have a face here, then a small Wilson loop around the face is going to be like part of poly z on the edge around the face. So it's going to be product of some of face, and then have product of poly z. Okay. Okay. So one term tells you that the low-energy state will satisfy the Gauss law, and the second term tells you that the low-energy state will have zero flux, namely the gauge field is flat. Okay. So, and we can check that each of the terms commute with each other. So, for example, if you have a vertex V, which is at the corner of this face, then this part of X term and the part of Z term will have a pair of edges that overlap with each other. Maybe let me just so let's say you have a vertex V at the corner of this face. Then this part of X term, this Gauss law term, is like part of like 4 poly X on this orange dash edge, and can show that there are a pair of edge that has overlap. So because each edge gives you a -1, a commutator between poly Z and poly X, and you have 2 edge overlap, so it gives you +1. And therefore, each term in the Hamiltonian commute with each other. So each term commute with each other. Okay. And therefore, you can simultaneously diagonalize like every term in the Hamiltonian. So this is called a poly-stabilizer model. And so I should define the operator W and M that I mentioned earlier. So recall that W is the Wilson line of the gauge field. And for the Wilson line defined on some on curve gamma, this is going to be the product of poly Z operator because poly Z operator is the gauge field. So it's going to be product of poly Z operator on the edge along the curve. So maybe I should okay. Okay. So if you have so let's say if we have I should use a different color. So let's say if you have a curve that extends, I don't know, maybe like this. Okay, this is your gamma. Then this W operator is just given by the poly Z operator along the curve, like poly Z, poly Z, poly Z, poly Z, poly Z, poly Z. Okay. So, and similarly, the operator, the Wilson operator for the dual gauge field is going to be a product of poly X operator. Not sure if I have an E here. So let me use a different color. So it's going to be a curve on the dual lattice. So this is my what's notation? This is my gamma dual. Okay, so this is on a dual lattice, and this curve on the dual lattice will intersect many edges on the original lattice, and this M operator is the product of poly X operator on the edges that are intersected by this curve on the dual lattice. Okay, so that's this W and M operator. Now, importantly, if those loops are closed, then they are symmetry of the Hamiltonian. So if gamma is closed, then can show that the Hamiltonian commute with this with those Wilson line operator. This is W. And similarly, if gamma charge is closed, and then the Hamiltonian will commute with the this operator. So now let me just introduce a terminology. So because it's a symmetry of the system, and moreover, it's a symmetry supported on some manifold of like lower dimension. So it does not support on the entire lattice, but just on some like lower dimensional some manifold. It's called a Hive symmetry. It's called a one-form symmetry. So because gamma, the support of the symmetry has codimension 1 space, have codimension 1, codimension 1 in space. Okay, so it's just a terminology. Okay. So now let me talk about what happens when the this curve is open. So when a curve is open, it's going to create excitations. Let's see. Maybe let me. Are there any questions at this point? Okay. It should be pretty old material. Can I use this? Okay, thanks. So if you have a curve gamma lies open, so let's say, so let me still draw some lattice. Okay, let's see. Okay. So if you have a curve gamma lies open, so let's say gamma is here, here. Then this operator W of gamma is not going to commute the Hamiltonian because this gamma is not closed. But only, well, let me draw it longer just to illustrate. Okay, but only, let's see, so this is here, this is restore here, okay. So this operator W of gamma does not commute with the Hamiltonian if gamma is like this with a boundary, with two boundaries. But in the other bulk of this W of gamma operator, like for these segments not like far away from the boundary, it still commutes with the Hamiltonian. The operator only does not commute with Hamiltonian like near the boundary, so other boundary points. So this tells you that this operator creates excitations at the boundary. So create excitation at the boundary. Okay. And because W of gamma is the Western of the Z2 gauge field, so this excitation is going to be the electric charge excitation. Electric charge. Okay. And one way to see this is that the endpoint of this W operator does not commute with the Gauss law constraint. Okay. So if you start from any ground state and apply an operator that create this pair of excitations, this resulting state, we're going to have energy coming from this Gauss law term in the Hamiltonian. And if you have energy coming from the Gauss law term, that tells you like you have some electric charge excitation. So here you have electric charge excitation at the endpoint. Now, importantly, it does not matter how far. So you can create the same pattern of excitation using another string operator. So for example, let me use a different color. You can, maybe let me use just white. So you can also create the same excitation using another string operator such that the original string operator and the new string operator form closed loop. So in this way, the energy only depends on the endpoint. It does not depend on like how far those excitations are separated. So these excitations are deconfined. So deconfined. Mm-hmm. So far, there's no boundary.
Okay, so when does the open
The open curve does not commute Hamiltonian. So that's why it has that's why you have excitation. Okay. Oh yeah. But right. Sorry. Okay, sorry. I should draw. So this is like huge lattice, and just have an open string operator here. Yeah. So it's deconfined because the energy cost does not depends on the separation of the excitation. Yeah. So the energy cost only depends on like you have two boundaries, then you have like energy cost 2, but it doesn't matter how far they are separated. Yeah. So that's why it's deconfined. Okay. So similarly, you can let's see. Right. So similarly, you can define the magnetic excitation. So in the completely similar fashion. Yeah. Okay. Let me just draw. Let's see. Okay. Let me just draw on the same lattice. So in a similar fashion. So suppose you have a open string operator for n. Then you'll have excitations on the boundary. So those excitations are called the magnetic excitation n, because so those open string operator will be product of like the poly X operator on the edge that intersect with this open string. And if you have this this poly X operator near the endpoint, this operator does not commute with the fluxure of this product of poly Z operator in the Hamiltonian, and therefore it has energy cost. And that's why you have excitations on the boundary. And again, the bulk of the string operator does not create any excitations because the closed, if you have closed string operator, it commutes the Hamiltonian. Only at the endpoint, the string operator does not commute the Hamiltonian and create excitations. So we have pair of M excitation here. And similarly, the energy of the excitation does not depend on how far they are separated. So it can move this excitation further away, but it does not cause extra energies. And therefore, both the E excitation and M excitations are deconfined excitations. Okay, so now let me illustrate the braiding. So let's imagine you create a E excitation. So let's say you create E excitation here. So you have a excitation here created by some like open string operator. And you can try to move a thanks. You can try to move a M excitation around. So recall that an open string operator, like this open string operator for this M, create a pair of M excitations. And particularly means that if you start with a state that already has an M excitation on its plaquette, and then you apply this open string operator, you'll get a state where the excitation does not sit here, but actually sit there. Okay. So in this way, you can use the open string operator to move the excitations around. So for example, so let's say you start with a state with a E excitation sitting on this vertex, and it can be obtained from the ground state by applying this open string operator part of Z. So, and then you can try to move the M set. So you can start with a so let's say you start with a pair of M excitation, which is generated by like this short open string operator. And then you move the other excitation around this E excitation until it comes back to itself and annihilate. Okay. And this string operator that implement this motion is going to be a closed loop operator that surround this E excitation. So that's part of X here, X here, X here, X here, X here, X here. Yeah. Now, because this E excitation is generated by like product poly Z. And can see that this loop of the string operator on the dual lattice for moving the M excitation will anti-commute with the string operator to create the E excitation. So let me just write down. So like W and N. So let me just switch the colors a bit. So there's a minus sign, and then have a N and W, and W here. Okay. So you can see that if you imagine, if you think about this in terms of space-time picture, so we have an E excitation here is like extending, is extending along the time direction. So imagine there's a time direction like pointing outward. Then there's a braiding between this, braiding between the word line of this E excitation with this trajectory of the M excitation. So this is like a braiding here. You move M around, have a E here. And the braiding give you a minus sign because the poly X and poly Z operator does not commute with each other. So that's the illustration of braiding. Okay, so now let me discuss the boundary condition. So maybe I may erase this. So I'm going to, well, let me first discuss the notion of condensation. Okay, so just quickly condensation. So let's discuss what happens when we condense the electric excitation. Okay, so condense the E excitation. So what it means is that we start with the original Hamiltonian. So I'm going to use this TC to denote the original torical Hamiltonian for the Z2 gauge theory. So we have product of X, product of Z. So that's the original Hamiltonian. And for if you want to condense the E excitation, you just add a term in the Hamiltonian with a large coefficient, where this term is generated by like pair of the E excitation. So here is generated like pair of the E excitation on every edge. If you take the coefficient to be very large, take it to be large. Okay. Now, what's the result of the condensation? Now, because you take the coefficient to be very large, so effectively you are going to obtain the Hamiltonian such that the terms commute with this XE operator. So only terms in HTC commute with this XE will survive. And also, because you add this term with a very large coefficient, so you also have to impose like SE equal to 1. Okay. Now, because the Hamiltonian term, let's see, sorry, this is, okay, let me just switch this a little bit. So here I'm condensing E, and E is generated by the poly Z, so this is poly Z, actually. So this is poly Z. Z will survive, and also the poly Z equal to 1. Okay. Now, this product of poly X operator does not commute with the commute with the poly Z operator, so all this Gauss law term will disappear, and you are left with the flux term in the Hamiltonian. Now, on the other hand, because we already demand that all the poly Z operator has to be trivial, so that means that this remaining flux term will also be trivial, like a constant. Okay. So that tells you that after you condense the E excitations, you actually got a trivial Hamiltonian. We actually got a trivial system. Now we can use this idea to construct a gap boundary. Okay, let me just erase this. So the idea is that we start with the original model, and then we are going to condense the E excitation on half space. So we want to condense E. So this is the original model, and I'm going to condense the E excitation. And because the E excitation, because after condensing the E excitation, the theory becomes trivial. So we have trivial theory here, and we have a little gauge theory here. So maybe let me just swap the ordering just to compare with the previous discussion. So I'm going to condense E here, and this is the original Z2. Okay. So after condensing the E excitations, I got the trivial theory, and here I have the original Z2 gauge theory, and here I have a gap boundary. Okay. So let me write down the explicit model after I perform this condensation. So recall that after the condensation, we can only keep terms in the Hamiltonian commute with the this terms that generates the condensate. So the original Hamiltonian term. So let's say this is your boundary, and then so let's say original Hamiltonian you have this like product of x term. But this product of x term is not going to commute with the poly-z operator because if I have poly-z here, it does not commute with the poly-x operator. So we cannot have a Hamiltonian term like this. The Hamiltonian term only consists of the Gauss-Law term, which are like sort of like this, where like the vertex is away from the boundary. Okay, so that's the allowed Hamiltonian term. And you can still have the Hamiltonian term, which is product of z. Okay. So this is going to be okay, but because we already set a poly-z operator on this half space to be 1, so you can ignore this poly-z operator in the Hamiltonian term. Okay. So this gap boundary is described by modifying the Hamiltonian term near the boundary, such that you don't have any this Gauss-Law term that close the boundary. You just have the Gauss-Law term here. And the flux term, you can modify to be like without this extra h here. Okay. Right, so the reason the boundary is gap is that you can check that those modified Hamiltonians still commute with each other. So you can diagonalize every term simultaneously and find out there's a gap. Yeah. So for example, if you have a so if you have a flux term like this, it still commutes the star term here because you have a like poly x here, and then if this corner overlap with the vertex here, this pair of edge overlap with the edge here, this edge overlap with the edge there, so you have two minus signs, so they still commute with each other. Yeah. Okay, so this is the this is one example of gap boundary. Now, what's the property of this gap boundary? So I'm going to say that this gap boundary corresponds to condensing the E particle. So here we're condensing the E particle on the half space. In particular, we condense the E particle on the boundary. So one way to see this condensation is that suppose suppose we have an excitation in the bulk, which is the E excitation. We can move the excitation to a boundary and then disappear. So we can apply a poly-z operator that terminates on the boundary, such that this poly-z operator only creates excitations at this endpoint, but not at this endpoint. So the reason is that the poly-z operator commute with the Hamiltonian term near the boundary. So you can see that near the boundary, you just have this Gauss-Law term, and then you have like even number of so let's say this is your vertex here, this is your vertex here. And this string operator overlap with the Gauss law term by two edges, and therefore it commutes the Hamiltonian near the boundary. And therefore, this string operator can move the excitations in the bulk to the boundary and disappear. So that tells you that the elastic excitation condenses on the boundary. And similarly, you can define a model where you condense the M excitation on the boundary. So you can condense the M excitation on this half space, and then you can similarly modify the Hamiltonian terms to get the gut boundary for condensing the condensing the M excitation. So that's the gut boundary. So another thing I should mention is that the model also has the electromagnetic duality symmetry. Okay. So because the elastic excitations is created by the poly Z operator, and the magnetic excitations is created by the poly X operator, so electromagnetic duality symmetry is going to change the poly Z to poly X. So you can think of about say could be rotation on every edge. Just swap it Z and X. And however, if you look at a Hamiltonian and then just swap Z with X, like if you replace X here with Z and Z here with X, you'll find out you got the original Hamiltonian but on the dual lattice. So the electromagnetic duality symmetry is not just swapping Z with X, but you also need to compose with a translation. So by the way, this operator can be implemented by the Hadamard operator. So 1, 1, 1 minus 1 square root of 2. Okay. So if you conjugate poly Z by its Hadamard, then you got a poly X and vice versa. So because you have to swap the lattice with dual lattice, so the electromagnetic duality symmetry has to be given by this Hadamard composed with lattice translation by 45 degrees. So let me erase this. So so this is where you put your compute. So if you originally have like poly X operator, and so by conjugating with this edge, you change it to be poly Z operator, but then you can translate to be like by 45 degrees to be the poly Z operator here. Okay. So well, I mean, can try to. So you have to go between the lattice and dual lattice such that you got the model defined on the same lattice. Yeah. So just double check. Right. So basically, this is well. So far I have just told you how to realize the ingredient of the Z2 gauge theory 2+1 dimension on a lattice using the historical model. I think this is a natural stopping point. Are there any questions?
So this the area picture is what we went through.
Yeah.
The ion will be your
That's right.
And so previously we wanted to know the boundary of
Mm-hmm.
which is like a physical 2D theory with the C.
Right. Right.
Can we do that in the lattice?
Yeah. So for example, on the so for example, this construction of a gut boundary, or they give you a like system, like can think of this boundary as say like 1D system on the boundary with a Z2 symmetry. So Z2 symmetry will be joined by like this M operator, product of poly X. Yeah.
And since it's on the lattice,
Mm-hmm.
like a constant pattern,
So I mean the boundary is like a long line. It's like it's 1+1D. Yeah. Right. So let's right. Yeah. Mm-hmm. Yeah.
previously example, there was this H item model. Do you look at one-dimensional H theory to operate this item?
You have to do some truncation. So, so here I give you some example of gap boundaries. So those are like complete gap boundaries without interesting dynamics. But you can truncate the lattice in a different way. So like you can truncate lattice by like 45-degree or some other shape, and then in general you got non-trivial dynamics. Yeah. So for some, for some truncation you got the icing. Yeah. So I guess I will stop here. Thanks for coming.